Rule number 5 is the product rule. So what is going to happen now is sometimes you have a function that is the product of two things. X plus 3 times x plus 5. And up till now, we just multiplied that out to find the derivative, because this one isn't hard to multiply out. You could get x squared plus 8x plus 15, and then you could do the derivative. But the question is, what happens if it's not fun to multiply out? Let's say your functions are x to the 5 minus 3x squared plus 6, and then you have x to the 4 plus x cubed plus x squared plus x plus 1. You could multiply that out as well, but it wouldn't be, well, depending on your definition of fun, it would just be tedious. It'd be long. Okay? And so the question is there a rule for derivatives when you multiply? Now, famous mathematician Leibniz said, well, what do we do when we add? We just find the derivative of each thing separately. So Leibniz thought, wouldn't it be nice if we multiplied, we could just find the derivative of this one, just find the derivative of this one, and then multiply our answers together. That seems like a logical first guess. It was wrong. Okay? You can probably see it in our first example here in the green box, right? If you multiply it out from here, the derivative would be 2x plus 8, right? If you did the derivative of the first one, you just get 1. Do the derivative of the second one, you would get 1. 1 times 1, 1. That is wrong. It would sure be nice if I could just do the derivative of this one and the derivative of that one and multiply and have it work out, but it doesn't work. You have that in your notes as an example here as well. Something simple. Take x to the 5th. You know that the derivative is 5x to the 4th. But if you broke it up to be x and x to the 4th and did the derivative of each of those separately, you would get the wrong answer. So we were really hopeful if we were multiplying two things that we could just do the derivative of one times the derivative of the other one and everything would be good, but it doesn't work. So Leibniz had to go back to the drawing board and say, maybe there's something else that I could do that could make this work. And sure enough, he figured it out. Are you ready for the next slide or not quite yet? So what did he come up with was this. All right, if you have two things multiplied together and you want to find the derivative, this is what you have to do. What does this mean? You keep one function the same and multiply it by the derivative of the other function. And then you add the derivative of that first function multiplied by the derivative of the other one. And we have two different notations. We have Leibniz's notation and Newton's notation to look at this. So what does this mean with the example that we started with? Okay, I'm going to erase this big one. With the example that we started with, we could have multiplied it out and got the answer to be 2x plus 8. In Leibniz's new rule, he says you can find the derivative by keeping one the same. So let's keep x plus 3 the same and multiply by the derivative of the other one. What's the derivative of x plus 5? 1. Then keep the other one the same, x plus 5, and multiply it by the derivative of the first one. That's the derivative of x plus 3? 1. Multiply that out and simplify. You're going to get 2x plus 8, which matches up with what we know to be the right one had we multiplied it out. Now, in this case, multiplying out is probably still easier. But if we get to more complicated ones, which we will, okay, then the product rule will be easier. And since we're adding, it doesn't matter the order that you do this. If you remember, I keep one the same and multiply by the derivative of the other one, and then add and switch it, you're going to be fine. It doesn't matter which one is first and which one is second. Keep the first one as it is, multiply the derivative of the second, then keep the second one and multiply by the derivative of the first. So here's one that wouldn't be hard to multiply it out. But if we use our new rule, okay, to find the derivative, keep the first one the same, derivative of the second one. Then keep the second one the same, derivative of the first one. Then if you wanted to, you can multiply things out, combine like terms, and simplify. Now, had you multiplied it out to begin with, oh, I don't want to do this. Never mind. You're not going to look at this part. There we go. Nope. There we go. Whoa. There we go. There. Sometimes I like to color code things so you can see, here's my first function, here's my second function. Notice my first function stayed the same, derivative of the second one. Then my second function stayed the same, derivative of my first one. Hello. I don't know if we've seen this notation yet, the d over dx of something. This means find the derivative of that. So the derivative would equal, again, if I color code things, right? I have my first function multiplied by my second function. Keep my first function the same, multiply by the derivative of the second function. Then keep the second function the same, multiply by the derivative of the first function. Again, you could multiply this out and simplify. Some of you are probably thinking, if I multiplied to begin with, I would just get x cubed plus 5x to the 5. Isn't this easier? And I would say, yes, it is. For this case, it probably would be easier to multiply out first and use your regular derivative rules. But it's nice to see that you get the same answer whether you use your new product rule or your old derivative rules, your old power rule. Maybe a little bit less fun to multiply out. This might be the first example where you actually say, yes, I think I might want to use my product rule. Again, color coding things. I've got my second function, my first function. What happens? Well, I keep my first function the same, multiply by the derivative of the second function. Then I keep my second function the same and multiply by the derivative of my first function. And do you know what's really nice in calculus? Is often if they say find the derivative, they do not ask you to simplify. So this would be all you have to write, and you're done. Which is, I think, sometimes the reason that calculus seems to be impressive. because this is the question, and then you just write this long answer, and the person looks at it like, if they don't know calculus, they'd be like, what did you just do? And you're like, I'm just smart. It's not that hard, right? The rules themselves aren't that hard, but if you just saw the answer and just saw the question, they'd be like, how did you know to do all of that? And that's where you don't tell them anything. Just let them think that you're super smart. And if you wanted to simplify this, you could. But like I said, most often you'd be fine just to leave it as the first line. You wouldn't need to simplify it. Here is the first really good example where you have to use the product rule, whether you simplify it or not. So we don't even have to simplify our answers. I would like you to try this one and the next couple. Yeah. Try all of these ones in example 4 and example 5 on your own. Put the answer up for the first one to see how you're doing. Did you remember that the derivative of natural log was 1 over x? Keep one the same derivative of the other one. Keep the other one the same derivative of the first. This one, there's no way that we could have done it other than knowing the product rule. This is good to test your memory if you've remembered these. Again, it is recommended that you memorize all of these. The derivative of sine is cos. The derivative of cos, negative sine. The derivative of e to the x, e to the x. So, does it make sense that the derivative of e to the x minus 1 would just be e to the x? And then we would have cos x minus sine x. Finally, example 5. This one does say simplify. So I'd recommend doing a bunch of derivatives for practice just because you want to have them memorized, and probably the best way to memorize them is just doing a bunch of questions. After you've simplified it, there's the final answer. So question 6, find the derivative. Okay, I'll give you a 10-second head start. Check how you did. And then in part B, when it says find the gradient of the graph at x equals pi, that means we're trying to find the slope of the tangent at that point. Our derivative is the function that has the slopes of all the tangents. So if we want to find it at x equals pi, we just have to plug in pi. And then it goes back to your pi plate and your unit circle. Do you remember what cos of pi is? What sine of pi is? Negative 1 and 0. And so the final answer is just negative 2 pi. We've got our function, and we want to find the slope of the normal at x equals pi. If you find the derivative, that finds the slopes of your tangents. So again, the first thing we're going to find is our derivative. You get that another 10-second head start. How did you do? And then, if you'd like, you could factor out an e to the x, not necessary, but you could if you'd like. If you want to find the derivative, if you want to find the slope of the tangent, you'd plug in pi. This just simplifies to become negative e to the pi. So what's the slope of our normal? We have to do the negative reciprocal. Do you like answers like 1 over e to the pi? Or do you feel like something went wrong along the way? It's kind of a pretty looking answer.